Welcome to the Australian Water School, the home of demand-driven industry design training for the global water sector.
Hi, and welcome to everyone attending today's webinar from all around the world. Today we are talking about how whips and ships are like weirs and piers. Well, it's Froude, dude. That's what our topic is today. How is the Froude number correlated to a number of different things that we might all be looking at as water professionals? Now, it has been a difficult week for everyone, I think, watching recent events unfold. There may be some attendees directly affected, and our thoughts are certainly with you. We were all warned years ago that future wars might be fought over water, and if you look at the role that water has played in this current conflict, that prediction may be coming to pass. We're hearing about missiles heading for dams that could cause cascading failures and some other catastrophic scenarios. It's absolute madness. We've also had some phenomenal rainfall right here in Australia that we'll talk about with our panelists in just a few moments. So let's dive right into introducing our speakers for today. So we have got Hubert Chanson from the University of Queensland, April Jennifer Choi. Look at where she's coming to us from the Kennedy Space Center. Bob Keller and Chris Goodell are familiar faces. So I understand there is some high water going on right now in Queensland. And I know, Bob, you may be affected with that a little bit in Victoria as well, but I know Hubert's been hit fairly hard by that. If you could just let us know, first of all, what's that picture behind you and what's going on right now in Queensland?
Look, the picture behind me, Chris, is the Indooroopilly Bridge at the peak of the flood on Monday morning. So the Brisbane River has peaked and is now declining, and we have had a fairly major flood. However, at the same time, there have been some very major events on the Sunshine Coast, but also on the Gold Coast, as well as two rivers in between Brisbane and the Gold Coast called the Albert River and the Logan River. The Logan River, which is currently near a peak, which is probably one of the largest recorded flood in history.
Wow. Yeah, I've been seeing some of these reports of 2,000 to 1 in 10,000 AEP events. This is phenomenal in certain places. There are intensities that have never been measured before in these areas. Our thoughts again are with all those who are dealing with the consequences of some pretty catastrophic flooding at the moment. April, I wanted to just mention last month we had a speaker come on, and he was a whitewater kayaker who was a designer, and I kind of joked with everybody, and I said, when you Google John Fenton's name, he came on. We had two choices. There was John Fenton, the whitewater designer, and John Fenton, the assassin, and we had to choose which one it was. Now this time around, if you Google April Jennifer Choi, you get a choice. Do you get the CFD modeler? Do you get the Guinness Book of World Records holding whip cracking expert? Do you get the violinist, the bassist, the dancer, the performer, fire eater? Did we get the right one today? And the answer to that is yes, all of them, because they're all the same person. She is all those things all wrapped into one. If you can just introduce yourself briefly and let us know where you're coming to us from today.
Hi, my name is April Jennifer Choi. I'm speaking from Orlando, Florida. Unfortunately, due to the pandemic, there is still a stage 1 evacuation for Kennedy Space Center. So they're having most of the staff there working from home where I'm at right now.
Wow. Well, that's yeah, we'll hear from Jennifer in a minute about some of the really cool things she has done and some of the videos that are out there and available to watch on YouTube, including, I'll mention this, she has got the coolest wedding photo of all time. It went viral, so Google that and have a look at that. Chris and Bob are familiar faces, but yeah, we on these webinars and in our courses, but we'll have you introduce yourselves nonetheless. Chris, over to you first. Where are you coming to us from this morning, or this afternoon for you, really?
Yeah, thanks, Craig. Happy to be here once again, and coming in from Portland, Oregon, and we're having our typical rain, but nothing like in Australia. But super excited here to talk about the Froude number.
Yeah, excellent. And Bob, over to you. Where are you coming to us from this morning?
I'm coming from Melbourne in Victoria, and we did have a shower of rain yesterday that's as heavy as anything I've seen in the 40 years I've lived here, but nothing like what Queensland's having, so we're lucky. My roof leaked a bit, which is not a good look for a water engineer, but that's life. And I'm an ex-academic and working as a consultant these days.
Sounds good. So I guess one of the things that I did want to mention about the poll results that show, first of all, the pronunciation of Froude is that Rude as in Froude, or Froude as in loud, Frud, fraud, Froude, Froude or Freud. And it looks like most of people are going to say Froude. That's how we pronounce it today, but we do have a Frenchman on board who may pronounce things a little bit differently. Also, I wanted to get a feel for whether you're familiar with a lot of the terms that we'll be covering in this webinar and some upcoming webinars. And it looks like there's some pretty good coverage of those those terms. And a lot of people have actually used some of their math skills in their work, which is actually more than I thought. People are actually using calculus in their work. I have to admit, it's been 20 years of water modeling, and I have not yet done a differential equation. So let's dive straight into our topic for today, which is Froude and the Froude number. Now, I've got a few analogies shown here. A ship wake, and we'll hear from Hubert momentarily about how Froude was actually a naval architect, and how does a ship moving through water behave like a bullet moving through the air or a supersonic jet, and how does that all relate to a bridge pier and a moving medium. So we've got sometimes mediums that move, and sometimes it's the object that moves within the medium. What we're doing with this topic today is introducing one concept, that's the Froude number, but we're trying to give you a feel for how our upcoming courses in May and June are going to play out. And we're going to address a whole lot of different terms in those courses. And we're going to take them all back to the first principles. You know, how does water behave like Newton's experiments here, and momentum and energy? How does gravity come into play? Hubert will mention in our equation today, you'll see gravity in there. What would happen if you took some of these models out into space? If you've seen the movie Passengers, they studied this intensely as far as how water would behave without gravity. And they used some of the International Space Station experiments to see how the surface tension would keep it together. And what would happen if you took your model out into space and then put it into a space elevator and accelerated it at 9.8 meters per second squared. It's the same thing as you would have here on planet Earth. So we're going to try and take all these things back to basics, to first principles. And one of the things that we're also going to talk about a little bit today is analogies, and some of the analogies that we've got. These are Wikipedia animations from the Doppler effect. And we all know that has to do with sound. But what does this have to do with water? Well, if you imagine a ripple of water and how fast that ripple travels, that's what we're talking about today. And so if I took that same Doppler effect, and instead of moving the object through the medium, I keep the object where it is and move the medium around that object, it really ends up being the same thing, and your perspective can come into play there as well. Now, we all have analogies every day that we deal with. Are we dealing with subcritical or supercritical flow on the road? Are you guided by just the traffic around you? Is this laminar flow? Is it turbulent? Are you dealing with backwater effects and waves from the brake lights that move up towards you? There are analogous systems all over the place. One of the ones that's most familiar, and we'll hear from Hubert about some weirs out there where we have some supercritical flow. Which direction can information move in? Can this fellow who's trapped in this vortex splash a message up to somebody standing up on shore here and send a wave upstream? That's what we're going to talk about today. Which direction can information travel in? Now, one of the things I wanted to mention is that we don't have time for to hit everything associated with this topic today, but what I've done in the background here is to set up a website called surfacewater.biz/Froude, and on that website we've got links to some of the cool videos that we'll be talking about today, to Hubert's open channel flow book, and then to the hydrology and hydraulics essentials course that will be that this will feed into. So with that, if I could get Jennifer, if you can turn your camera back on, and what I want to do here is just have you talk a little bit about one of these videos that you were on, and this is a channel online that's got lots and lots of subscribers. I'd recommend everybody subscribe to this one as well. It's called Smarter Every Day. And yeah, Jennifer, if you can just or April, sorry, if you can just explain a little bit about what you did in here and what some of the findings were on this show. So we got 2 episodes. One of them was about bullets in the air, and then another one about whip cracking.
I had the wonderful opportunity to work on an experiment with Destin from Smarter Every Day on Schlieren imaging, which is specifically how you viewed pressure variations in the air using a technique developed by Schiller, where you can see the densities of the air translate. So as Cray was saying earlier, you have a natural propagation of pressure waves that would occur in water as it would oscillate up and down, or as sound travels away from an object in a medium of air. So in the instance of a bullet, we have something that's referred to as the Mach number, which is similar in the Froude number, in the idea that once you reach a certain point, in this case being 1, since it's a dimensionless number, there's amount of propagation that can occur forward as well as sideways. So as these waves try to propagate sideways, so an up and down in the visual frame of reference to what you're seeing on the screen, you can see in the lower left one that a supersonic bullet will actually travel faster than the propagating wave that travels at the natural speed of sound. This is how you get that supercriticality, or those the Mach number higher than 1. So in the lower right-hand corner, you can see what happens when you go from a transient flow, which allows some areas to be supersonic and some areas not, and then you're breaking the sound barrier, what a lot of people refer to, and that's creating this Mach angle that's coming away from the tip of a bullet. So I flew down to Mississippi to help with imaging, where you can see the flow of a bullet through air, and then my big passion in whip cracking also got to get utilized to be able to actually see the development of a shockwave come off of a whip. So a lot of people know that cracking a bullwhip breaks the speed of sound, but we've never actually seen how that functions. So for this time, we were able to use an Atom Lab, which is a laboratory designed to capture the 3-dimensional kinematics of objects. So we could actually track the kinematics of a whip. And then we actually get to see the wave propagation down the whip, as well as using that Schlieren imaging I spoke of early to actually see the bow shock development come off of that whip. So you can see how that whip is moving. And one thing that we also got to see is being able to see the different pressure variations to actually see the development of a denser air bow shock in the front, as well as dissipating toward the back end. And this was an incredibly fun experiment here, where we did get to talk a little bit more about the Eulerian-Lagrangian framework, on whether or not you would take the framework and look at the object you were tracking. So if you were just standing, looking at a bullet, for example, driving in a car in traffic, versus if you were standing on the bridge pier and watching traffic flow below you, it concentrates whether or not you're the object itself or the flow field around you.
Awesome. So one question then for you is, when I'm at the gym and I use the battle ropes, how come those don't crack? What about the shape of a whip? And maybe this is a hint at the conservation of momentum, perhaps. What is it about the shape of a whip that makes it crack on the end?
So it's not necessarily the shape of the whip. So I ended up cracking a whip that was over 350 feet long, though it did look fairly similar. It was about 111 meters for those who are using metric units. And though for much of the whip, the diameter stayed the same, I ended up using different materials to vary the density so that the mass density actually ended up decreasing. So it's that mass taper of the whip that's generalized, that actually helps it accelerate it due to conservation of momentum, because you have the mass times the velocity. So you actually change the materials by placing steel BBs inside a whip, and then that actually decreases in size for those BBs to be able to decrease the mass density much faster than just the diameter.
Awesome. So this is just a preview of what April's going to bring to the table. We're going to come back with more of these first principles in May in a webinar that we'll be doing then, that's going to get a little more in depth onto some of the wave equations and things like that. But there are analogies everywhere, and sometimes it's easier to picture things that you might be able to imagine every day. Do watch these episodes with the sound turned way up so that you can hear the whip crack, because gracing us today is April, who is the Guinness Book of World Record holder for the loudest whip crack ever, I believe. Is that correct? There we go.
That is.
Okay, awesome. So keep your questions coming for April and for any of the other panelists as we now switch over to Hubert, who's going to introduce the concepts and the equations that underlie the Froude number, and then we'll talk about what that means for your hydraulic modeling. So over to you, Hubert.
Thank you very much, Chris. Thank you very much, everyone. Let me get started here. So this talk is really to rush or not to rush. Apologies. I will start with an apology. I'm talking to you from home right now because our university campus is underwater and is closed for all this week, and I hope the internet will go well. So I will start by asking you two questions. The Froude number equal unity mean critical flow condition, true or false? And then the Froude number is derived from energy considerations, true or false? Think about it, and we'll come back to this question at the end of my talk. The Froude number is a dimensionless number that is linked to gravity effect and is often defined as the ratio of the velocity scale divided to the square root of the gravity acceleration time length scale. It is named after an Englishman, William Froude, who used this dimensionless number in the 1870s. But in fact, the dimensionless number was first introduced by a Frenchman, Ferdinand Reich, who was an academic staff as a French naval academic, and used this dimensionless number for the testing of ships and propeller, introduced first in his lecture note in 1832 and later published in 1852. Interestingly, about the same time, a number of hydraulic scholars in France recognize the significance of this dimensionless number in relation to the various open channel flow regimes. And in France, many textbooks will refer to this number as the Reich-Froude number. And indeed, when I was taught at university, I was taught about the Reich-Froude number. Maybe first, one of the key takeaway messages this morning. The Reich-Froude number may be derived from several different fundamental principles, all of which are theoretically correct. It may be derived based upon dimensional consideration, using, for example, the Pi-Buckingham theorem, because the gravity effects are always important when we are modeling free surface flow. And you see in front of you a picture of a 25:1 ship scale model. Don't be fooled by the scale. This ship model still weighs between 5 to 8 tons. We may also express the specific energy in a dimensionless form and derive critical flow condition for minimum specific energy following the work of Boris Bakhmetev. We may also derive the Reich-Froude number from momentum consideration, either from an integral form, such as the Bélanger equation, or from a differential form, such as the Navier-Stokes equation. The equation in front of you, the Bélanger equation, applied to hydraulic jump in horizontal, smooth, rectangular prismatic channel. And it was derived first in 1841 by another Frenchman, Jean-Baptiste Bélanger. We may equally derive a Reich-Froude number based upon energy considerations, either in an integral form or in the differential form. And many of us today will be familiar with the differential form of the energy equation called the backwater equation. Maybe the second key takeaway message today is that since the Reich-Froude number can be derived from several different correct theoretical considerations, there are in turn several different definitions of the Reich-Froude number. If in front of you 5 different definitions, and I know at least another 3 to 4 other definitions. So here, as hydraulic engineers and fluid modelers, we need to ask ourselves, which one is the correct one? Which one should we use? How to define the Reich-Froude number? And the answer is reasonably straightforward when we go a little bit deeper. In open channel flow, the most pertinent, if not the most correct, expression of the Reich-Froude number is the ratio shown in front of you, where the characteristic length scale is the ratio of the cross-section area to the free surface width, with both the cross-section area and free surface width being measured perpendicular to the streamline, that is perpendicular to the flow direction. Interestingly, this definition in front of you can be derived from both energy and momentum principles. With this definition, and only with this definition, the Froude number is equal to unity at critical flow conditions, when D equals dc, D, the water depth being equal to the critical depth. When the water depth is greater than the critical depth, that is when we have a subcritical flow, then this Froude number definition will be less than unity. And when the water depth is less than the critical depth, that is we have a supercritical flow, this Froude number will be greater than 1. The concept of critical, subcritical, and supercritical flow are essential in open channel hydraulics. I'm playing a video, and I hope you can see it, of a spillway operation in December last year in Queensland, with subcritical flow in the tailwater condition, a hydraulic jump, supercritical flow down the steep chute, and critical flow condition at the spillway crest. This particular video that I will replay was observed at the beginning of the flood. 2 weeks later, this dam was completely overtopped, and on the right, the two photographs illustrate the high water level, and my car will have been completely submerged at the time. So coming back to the two key questions at the start of this talk, a Froude number equal 1 mean critical flow condition, true or false? The answer is false, unless we use a definition of the Froude number as shown here, using the ratio A over B as a characteristic length scale. The Froude number is derived from energy consideration, true or false? I will say mostly false, because we can derive the Froude number from momentum consideration as well as dimensional consideration. So, as we are at the end of this talk, let's focus on the key outcomes. The Froude number is a dimensionless number, which may be derived from several different theoretical considerations, all of which being correct. In turn, there are many definitions of the Froude number, and so there is only one which is relevant to flood modeling, the one shown on the top right of the screen. For those interested, there is a number of bibliography that you may wish to check. Thank you very much.
Excellent. Thank you so much, Hubert. Over to you, Chris, if you can start sharing your screen. Look forward to hearing from you.
Okay, here it comes. So yes, thanks, Professor Sanson. That was awesome. Very good. I know we don't have a lot of time. I'd love to hear you talk about this for another hour or more. So I'll definitely be checking out more of your videos. But I want to get into the practical side of Froude number and how we can use this to benefit our efforts in hydraulic modeling. So just really quickly, just to summarize what we heard from Professor Sanson, the Froude number is a ratio of inertial forces to gravity forces, or you can more simply define that as the velocity divided by wave celerity. Froude number greater than 1 is supercritical flow. Froude number less than 1 is subcritical flow. And if you end up at unity, we have critical flow conditions. So in considering computational hydraulics, when we're running our models, if you're in subcritical flow, gravity waves can travel both upstream and downstream. But in supercritical flow, those gravity waves cannot travel upstream. They can only travel in the downstream direction because the velocity is so strong compared to the gravity wave that it washes it downstream. And so on that spillway that Professor Sanson just showed, if you were to put some obstruction on the spillway chute, you would not see a wave propagate upstream. In stream modeling, natural streams, we generally don't think about the Froude number too much. And the reason for that is because most natural streams flow under a subcritical flow regime. However, understanding Froude numbers and noticing when your Froude numbers get close to 1 or even greater than 1 in your results can indicate some problems with your modeling inputs. N values are too low, possibly. That could drive your depths down below critical depth into the supercritical realm when maybe it shouldn't be there. Computation nodes may be too far apart. Either your cross sections are spaced too far apart, or you're in a two-dimensional model, your cells are too big, or high Courant numbers. You see high Courant numbers, that could be an indication velocities are too high and Froude numbers are too high as well. But not all models that we do in hydraulic engineering are natural streams. We get into constructed channels as well, which I'll talk about in just a second. But why should we care about the Froude number when we're doing our hydraulic modeling or hydraulic design? Well, I think it gives a better understanding of the conditions you're modeling, helps you to understand and interpret your results better. It can help verify whether your model is representing reality. Model stability as well. If you've been doing unsteady flow computations, whether it's 1D or 2D, you know by now that the acceleration terms can be very sensitive when your Froude numbers get close to 1 or even greater than 1. And that can require some additional measures be taken in your modeling efforts to make sure your model doesn't blow up on you. When talking about design, the Froude number can really help you in determining the expected turbulence you might have in a hydraulic jump and stilling basin design. It can give you an indication of how much uncertainty you may have in your results. It can also help in determining the required wall or bank heights needed to pass flow safely without overtopping the banks. Anytime you have Froude numbers that are really high, greater than 1, scour should definitely be a consideration because high Froude numbers tend to erode alluvial streams. And then there are considerations certainly for supercritically designed channels, and those do occur. You have steep slopes and you need to get rid of the water as quickly and as efficiently as possible. You may design it as a supercritical channel. Now, in these channels, there is a preferred range of Froude numbers coming from research. When your Froude numbers are near 1, this is a very unstable situation. If you look at the specific energy plot on the right, you can see the subcritical realm up here on the top, supercritical down below. This represents critical depth at your minimum energy point. When you're close to critical depth, notice the curvature on this plot. Okay, any small change in energy can create a large change in depth. And we typically don't want to see that when we're designing channels. We want to be able to be confident in the flow that we're going to have and the water surface elevations we're going to have in these channels that we design. Also, when Froude numbers get really high, when they get down on this end of the curve right here, we can also have unstable conditions, development of roll waves induced by very small influences on the flow. Even a small obstruction or a small disturbance in the flow can have significant changes in the depth of water and the characteristic of the waves on top of that water. So research done by the Army Engineer Research and Development Center, ERDIC, in Mississippi, they've suggested that for supercritical channels, you want to try and get your Froude numbers between 1.13 and 2 for optimal conditions. Now, this is an example of a one-dimensional model, unsteady flow model. And I'm going to animate this in a second, but what I first want to point out is in this completely drowned out situation, here we've got the water surface very high, completely drowned out, very subcritical all throughout this. The red line represents critical depth. Notice that the red line here, critical depth does not change with slope, and that's because critical depth is not a function of bed slope. Okay, so it's the same all throughout. But what is a function of slope is the water surface and the computed profile that you get. So when I animate this, notice that as we start off, we have supercritical flow on the steep section. We've got a jump, hydraulic jump here into subcritical flow, and then a transition back into supercritical flow where the bed slope becomes steep again. Now, if we were to put a disturbance on this supercritical slope, you would not see a wave propagate upstream. But if you were to increase the height of that disturbance or the blockage of that of the channel here, you would see a hydraulic jump form, jump into subcritical, and that would progress upstream until eventually this becomes fully subcritical. So now as we increase that disturbance height, you can see it's, oops, sorry about that. You can see that we've got a subcritical realm right here. It's still supercritical, and notice that this is not translating up through the supercritical reach until this continues to grow higher and higher. So as we progress through, you can see the downstream disturbance is getting higher. It's forcing everything into subcritical, and then we lower it back down and we come back to the original profile. Now, one consideration where you would want to think about Froude numbers is the design of bridges, because depending on the regime you're in, whether you're supercritical or subcritical, can have different effects on what's happening inside of the bridge. Here we have an elevation view of a bridge. This might represent the abutment of the bridge or maybe a bridge pier even. But in any case, we have a contraction of flow as water's approaching this bridge, going through it, and then it expands out on the downstream side. If we have a Froude number less than 1, fully subcritical, this is class A flow here, you can see as it goes through the constricted or the narrowed section, we have a drop in water surface. As it exits the bridge section back into the natural channel and it widens out, then we raise back up. And this is the associated head loss between the upstream and downstream. Now, what if we had fully supercritical flow coming? That's this class C, Froude numbers greater than 1. As you approach and enter the narrowed section, the water surface will rise up. It may not jump to subcritical. It could stay supercritical in here, but it will rise up and then drop back down on the downstream side. So this can have an impact on how you design this bridge and where you locate the soffit of your bridge, how high it needs to be, depending on how high this may jump up in a supercritical channel. I mentioned earlier that the Froude number can give you an indication of whether or not you have bad input data. Let's take, for example, we have a natural stream, but we put in an N value that's more characteristic of a concrete constructed channel. We might have water that shows up as supercritical. Here you can see the blue line, which is your water surface, and the red line is your critical depth. So here we're supercritical with the Froude number equal to 1.5. We add a bridge in here and you can see the jump up, as I mentioned in the earlier slide. Now, let's say that N value was wrong. This is a natural stream. It should be more something like 0.035. Notice that the red and blue lines are flipped. Here we have the blue line above critical depth, meaning we're in subcritical. You can see the Froude number is less than 1. And in this case, the same bridge added into this simulation created a decrease in the depth. Now, upstream of this, because this is subcritical, you actually have a rise. And so the depth up here is greater than what you have over here. And this is why when we put in a bridge, we typically see a rise and a backwater effect upstream. Consequently, if we have this bridge in here and we take it out, this dip will go away and you actually get a localized rise in the water surface for removing or widening a bridge. Here's another example of a hydraulic jump coming through a bridge. In this case, this is a two-dimensional model. Up on the top, we have our Froude number plotted upstream to downstream. Here you can see we start out with a Froude number around 2, and then it jumps. We have a hydraulic jump, so it lowers into the subcritical realm below 1, and then it transitions back into the supercritical downstream. In the water surface plot, you can clearly see where the hydraulic jump takes place and where that drawdown occurs to come back to the normal depth conditions. Here in the plan view of this bridge, you can see the abutments right here, and this gives you an indication that the hydraulic jump is not very uniform in when considering the changes laterally in this channel. You can see that there's a the jump happens further upstream on the sides, on the periphery of the channel, than in the center. It takes a little bit longer to resolve itself in the center than it does on the sides here. Another consideration for Froude numbers, if you ever get into the design of energy dissipation structures, the Froude number is very important because that gives you an indication of not only what the length of your hydraulic jump will be, but also the characteristics, the amount of turbulence you might see, and also the change in sequent depths from the upstream supercritical regime to the downstream subcritical regime. Notice here with a Froude number greater than 9, we have a very shallow depth, very, very high velocities, and a very turbulent jump into low velocities and greater depth. So this is something you would certainly want to consider when designing wall heights for a stilling basin, as well as the overall size and energy dissipation elements you might put into it. This is a figure right out of the Bureau of Reclamation's design of small dams, which has some different types of stilling basins you might use, or at least start out with for your design, depending on the Froude number that you have at the toe of the spillway. Here we have the spillway here. This is the stilling basin, which is meant to induce a hydraulic jump in a protected, armored section before delivering the flow downstream to the natural alluvium, where high velocities and high Froude numbers would tend to erode this material. So we want to keep the jump contained. That's why it's important to know the length of the jump, and the Froude number helps us to determine that, as well as how deep we need to put this or make this stilling basin in relation to the downstream river. So those are just a few things, few considerations in practice where you may want to use the Froude number. There are many more we don't have time to get to, but we'll get to that in the follow-up course. So back to you, Craig.
Yeah, we'll just have a panel discussion now about some of the questions that have come up. There's been some great questions asked. Those who are watching this YouTube recording later on will not see the questions. So if you do address a question, then just make sure you restate it. One of the questions that I'll ask here, and I think we'll start with Bob maybe for a response and then go to Hubert since you've answered this one already online. The question is, just wondering what a good way is to understand specific energy. So maybe we'll start with Bob and then go over to Hubert on this one. Looking at the specific energy plot here, are there any concepts that you've used in the past to explain this in your university lectures that help this to sink into somebody who's new to the concept of specific energy?
Yeah, okay. Specific energy is defined as the total energy relative to the bed. So it's the total energy, height of the total energy line above the bed level. I think looking at this diagram is a very good way to understand, and Chris did bring this out, that when you get near critical flow, which would be the nose of the curve, you have a rate of change of specific energy that is very small, but the depth increases rapidly for a very small change in specific energy. So that means that if you're near critical flow, then it just takes a small change in bed elevation to flip you from supercritical to subcritical, and hence give the large standing waves that are sometimes a feature of what we see, especially in some natural channels. But the one thing I did want to bring out is that we talk about critical flow as being something to be ignored. But if we have a look at the equation for critical flow, and it's not on the board, so just take it as fact from me, if you're prepared to do that, that the Froude number actually gives you a relationship between measured water surface elevation and flow rate. So if we can generate critical flow in a safe way, and we can do that with things like long-throated flumes, and also with a weir flow, a broad-crested weir. So if we can measure the water surface elevation at a point where we know the flow is passing through critical, then we have a relationship for flow rate. And that's the basis of a lot of our open channel flow measurement systems. The other point I wanted to make is that the instability at critical flow, if it happens in an uncontrolled way, is exactly the same, is exactly analogous to a Mach number or a Mach number of 1, which is the boundary between subsonic flow and supersonic flow. And I'm old enough to remember in the early 50s as a child hearing about the first jet planes that were crashing because they didn't have the power to push them through the Mach number equals 1 quickly enough. So the wings would drop off as the plane was juddering along at very, very close to the speed of sound, or trying to push through the speed of sound. And of course, nowadays, modern jet fighters just flip through it very, very fast with a huge boost of thrust. So you don't have that issue. But the instability in uncontrolled critical flow in hydraulics is exactly analogous to the Mach number of 1 in supersonic and subsonic flow. And of course, sonic flow is defined when you're traveling at exactly the same speed as the speed of sound.
Great. Excellent. Hubert, was there anything you wanted to add to that question about specific energy?
Okay, I think Bob provided some very clear explanation. If people want to go in more detail into how to draw such a graph that Chris has shown, I think people should need to go back to the fundamentals, how to calculate the total height, how to calculate the specific energy, how to calculate the relationship between the two.
Great. Excellent. What I'll do, there was another question that came up just asking about whether, what is a good analogy for, to explain to somebody who's a non-engineer, non-modeler, how do you explain the Froude number? And I think Bob said it perfectly there. I think everybody can picture, hearing a sonic boom as a plane goes by, where it's exceeding the energy. And I guess that would be the reason that we've brought April and others on here, is because that's a real world example that might be easier to picture. And so again, if this was the Doppler and the sound in the air, and if you imagine this being a rock dropped in the water, and the speed of the water going, the wave celerity versus the velocity of the water going next to you, really it's just a ratio. People say, hey, that plane was going Mach 2 or Mach 3, but we don't really translate that into our flow and say, hey, look at that river or look at that channel, it's going Froude 2 or Froude 3, but it's really the same thing. It's the ratio of the celerity of the wave, the information within the medium, to the ripple. It's the ratio of that wave that's moving to the speed of the water. And so if that water is going twice as fast as the ripples can go, like you see over here on the right, if it's going twice as fast as those ripples can move, then that might be a Froude 2. And so I think the Mach number is generally a good analogy for that. And it's something that's been brought up a number of times. I'd be curious then, April, if you wanted to mention to us a little bit about, this is a question that I actually looked up and tried to find the answer to. Does the space shuttle or other boosters or rockets, do they punch through the sound barrier on their way straight up? And if so, do you have some of those same issues when you're going up versus, you always picture a sonic boom coming from a plane going this way, but rockets, I think, push through it very quickly as well. Is that something you're involved in in your own professional work?
I'm not directly involved in the fluid dynamics of the rocket pushing forward. I do know that they exceed Mach 1 very, very quickly. And then there's also a point known as max Q, which is the point of highest dynamic pressure. And that's kind of the point, as people were saying earlier, that we worry about the most and hope that the vehicle doesn't disintegrate anytime soon.
Yeah, exactly. Because when you do have a standing wave, if you toss a rock into water that's moving at critical velocity, you would have a standing wave right where that rock hit. And so the same thing can happen as a plane is trying to punch through the sound barrier. It all kind of stacks up. What was interesting about those videos as well that April was involved in is that it showed that even something that's moving subsonically has elements and things around it that move supersonically. And so there's a bunch of particles around it. And that can happen in your hydraulic structure as well. When you fix a hydraulic structure and you move something around it subcritically, there can be supercritical pieces of it that pop up because relative to where your frame of reference, you might actually have some things punching through either critical flow or, in the case of a bullet, around that bullet, you actually have little pieces that go supersonic. Anything you wanted to comment on that, April?
That's a very, very good observation to make, is that anytime you have things that are in the turbulent regime, you have areas and velocities relative to your base inertial frame of reference that vary quite a bit. So you'll get areas that are transient where you'll see transient shocks develop.
Excellent. Chris, do you want to have a look? I don't know if you've seen some of these things that have come on since your presentation. A lot of questions have come in since you finished up. If you want to just pick one or two of these to highlight, and then we'll go back through the order again and just have everybody, if you could all just have a look through the questions. Try and hit the ones that have been upvoted the most, but maybe pick one to hit as we go through.
Yeah, so I've been answering those and keeping one ear on the conversation and one on the questions here. One comment that's come up a couple times is the software that I use, and many of you won't be surprised that it's HEC-RAS. Both 1D and 2D examples were shown. Let's see, what else did we have here? There's a question, and I'd be interested if to hear from our academics on the panel here, but Cameron Paynton from New Zealand wants to know, can we explain why a constriction on a supercritical flow results in a rise in water depth? Is the water slowing down through the constriction? So I provided a short answer there, but I wonder if that's worthy of more discussion here.
Yeah, I think, Bob, I've heard you give a lecture on this about an actual design case where you did this. Do you want to summarize that?
Yeah, I'm stretching my brain back a bit. It's a few years ago, but the I think that that specific energy graph is a very good one to show why the water level drops as you're going through a subcritical flow, constriction or a rise in the bed, and a supercritical flow, the water level rises. But basically, if you look at that graph, the specific energy reduces, the depth reduces quicker than the specific energy increases, is probably the best way of putting it in supercritical flow. So that means that you get a drop in the water level. Now, the analogy that, or the design case that I recall using was where you get you can get a subcritical flow going through a bridge site. And I had the experience of trying to persuade a council that if they reduced the width through the bridge site, they didn't have to make the bridge as high as they were planning to, because I said that subcritical flow will drop as you go through a constricted bridge site. Now, that's something that's intuitively not very clear, but if you look at that specific energy diagram, it is, because the asymptotic line for subcritical flow is at 45 degrees, which means that that asymptotic line means that the depth is exactly the same as the specific energy. And when you have subcritical flow, then as the depth changes relative to that line. In fact, you have a situation where the change in specific energy is greater than the change in depth, and so the water level actually drops through the bridge site. I had to build a model to persuade them that that would actually happen, and they got it after that.
Yes, it's no surprise that people tend to believe physical models over computer models sometimes, and seeing some of the results and instabilities that you might get in a computer model, that's perfectly understandable. Chris, one other question that came up, is whether on a dam breach, do you get supercritical flows? You said in natural systems, supercritical flows don't really happen, but in a dam breach, they obviously do in some localized areas. How far does that extend? How long can it stay supercritical before it goes back to turbulent flow?
Well, a lot of it depends on where the dam is and the terrain upstream and downstream of the dam. But in most dams that I've seen that have breached, you get a supercritical regime through the breach itself, and it quickly jumps just downstream of the dam. Of course, there's a lot of scour happening during a dam break if the bed's erodible, and so that can change things dramatically. You may start off with some supercritical flow that extends a little ways downstream, but then it eventually turns into subcritical flow as it scours a big hole in the bed. And so typically, obviously velocities are higher, depths are also higher. So the Froude numbers don't really get super high in a dam break moving downstream. You tend to get the really high the really high Froude numbers in constructed supercritical channels where they're designed to pass flow very quickly. The LA River is a great example, and we've all seen that in the movies. I think you've done some stuff on that too, Cray, on some of your videos. And so that's a great example of a supercritical channel where you can get some pretty high Froude numbers.
Yeah, excellent. But like you mentioned, Chris, and I think kind of a warning to put out there, a lot of times when you're looking at your model results, if it does go supercritical in a flood model, a lot of times that's just an indication of an instability in your model, and it might not be real, something to check.
Yeah, and another thing to point out too, when you do have a very steep and very dynamic flood wave moving downstream, it could be from a dam break, it could be a flash flood. The front end of that, or front edge of that flood wave, typically has a little bit of supercritical flow, or flow near critical depth anyway. And that's why it's very, very unstable to model that numerically anyway in a hydraulic model.
Excellent. All right, Hubert, I see you've been very busy answering some questions. If you want to pick one, and then April, we'll go to you after that. If you wanted to pick a question on here that you wanted to address, or another, something you wanted to highlight, over to you, Hubert, first.
So look, there was a question whether the sediment transport affect the Froude number or the definition of the Froude number. I think here, in a situation where there's no change in bed elevation and it's simply sediment transport by suspension, the fact that you have sediment is not going to affect much the definition of the Froude number, because the Froude number is not related to sediment concentration. However, practically, if bed scar or bed deposition or accretion take place, this may change drastically the entire process. And I'm going to use an example, which is the Brisbane River flood in 2011, where the water depth was typically between 5 to 10 meters. And in a few places, we had deposition of nearly 5 meters of sediment, while in other places, we have accretion of 7 meters. And in this case, clearly, we can no longer ignore sediment transport in the center of scour on accretion.
Excellent. Thanks so much. April, any questions that you've seen on there that you'd wanted to address? If not, I've got one for you.
Pendo Minha asked what's the difference between Froude number and Reynolds number. Froude number is the criticality. So think of how much propagation of information is happening away from something. In this particular case, the gravitational, the flow of the water as it's coming in versus the amount of total inertial bulk mass moving past. While Reynolds number looks at the variance differences between the velocity that the inertial frame of reference versus mass, well, not mass, that's the best way of saying this. So it gives a sense more of turbulence. So low Reynolds number is the laminar flow versus high Reynolds number is getting into the turbulent regime.
Awesome. The other question I had for you is, we've been talking 1D and 2D models for floods. I assume what you're using is 3D models, and it's kind of CFD modeling that you've done. If you wanted to just kind of to talk about the limitations, why couldn't you do what you do in 1D or 2D?
So one of the things that ends up occurring in a lot of CFD models is the areas of vorticity. And vorticity generates boundaries. So you have to have an idea of where those boundaries would occur so that you can get a vorticity model as things come over the shape of different objects. So in the case of like whips or plane wings, areas that are really concerned with are like, for example, winglets at the end of wings actually allow vorticity to come off the end of that wing. And that pressure variation makes sure that you have to actually know what the total length of the wing is, and then have a three-dimensional model to be actually see the vorticity shed off those wingtips and how it propagates backwards, not just necessarily the two-dimensional cross-sectional area of the wing.
Excellent. Yeah, and so one thing that sometimes isn't clear to people is when especially coming into university courses, when we hear the term computational fluid dynamics, or when we're talking about fluid dynamics versus hydrodynamics, some people don't picture air being a fluid. And so when we have CFD models, that fluid, that medium can be air or water or any fluid. And so, versus a hydrodynamic model for flooding, where the air is just kind of ignored. So there's a little bit of a difference there. What we'll do, we just have a couple minutes left, is just have everybody give either just a closing remark or hit one of these questions that you've seen here. We'll go back through the order again one last time, and then we'll call it a day. We might go just a couple minutes over, but I want to give everybody a chance to just give some closing remarks. Lots of great questions have come in. We may try to contact you individually with the answers. We've got these recorded now if we don't get a chance to answer them live. So maybe over to you, Bob. Anything you wanted to say to close up, or any other questions you wanted to hit?
Well, I guess one of the questions that came up, which I typed an answer to, just to expand on that a bit, was how do you determine if you're going to get a hydraulic jump, especially in an underground pipe that may be circular with open channel flow and so on. I emphasized in my answer that you actually can't determine it locally. You can't just look at a flow in a pipe and say, yeah, it's going to be, you're going to get a hydraulic jump or you're not, because I made the point that a subcritical flow is controlled from downstream, and that is because a small amplitude wave in subcritical flow can move in the upstream direction, and that's how you control a subcritical flow. Supercritical flow is controlled from upstream, and you must never make the mistake in design to assume that you can control a supercritical flow from downstream. You just can't do that. So to answer that particular question, how do you tell if a hydraulic jump is going to occur within a particular length of pipe? You need to treat it as a pipe problem and understand that whatever the downstream conditions and the upstream conditions are. It's not a local issue at all.
Thanks. Awesome. Chris, any closing remarks or last comments you wanted to address?
No, nothing in particular. I think this is a great discussion. Looking forward to more of that. Yeah, so thanks for having me on.
Awesome. Hubert?
Yes, maybe one comment. There have been several questions in the chat about the importance or the relevance of the Froude number for the design of hydraulic structure. The inflow condition may be sub or supercritical, and the resulting flow above or along or through the structure may be very different, whether the inflow conditions are sub or supercritical flow. Hence, for the design of any hydraulic structure, the Froude number of the inflow condition is uppermost critical, and equally, the Froude number of the tailwater condition may be also equally important.
All right, thank you. April, anything you wanted to say to close it out, or any other comments to address?
Nothing at this time.
All right. Well, thanks so much for coming on. Yeah, a few of these questions had to do with pipes. Keep in mind, if you're doing a 1D and 2D model, typically you won't be able to look inside of the pipe and see where that hydraulic jump occurs exactly. You might need a CFD model for that. The upcoming courses that we've got, we'll see some slides coming up with those as far as what you can expect going forward. But we're not going to be software specific for this hydrology and hydraulics course. So if you're a two-flow modeler, if you use Mike, if you use XP, Innovise, InfoWorks, any software at all, you know, OpenFoam, Flow 3D, Flow, any of those software, Flow 2D, any of the software packages. No matter what you use, what we found is that those who were signing up for some of these courses, some had an extensive background in hydrology and hydraulics, others need a bit of a refresher, and some are coming at it without any water background whatsoever. And so we want to have one repository of the best summaries and the best experts we can find out there to explain these things to you and put them all in one course series. So that's what you'll see then coming up in May and June. All of these terms that we talked about, conservation of energy and momentum and mass, the steady versus unsteady flow, if we're talking about laminar versus turbulent, the Reynolds number, Moody diagrams for pipe flow, rainfall and runoff, IFDs, intensity, frequency, duration, you know, rainfall runoff relationships. We're going to try and pack as much of those concepts as we can into this one course, giving you just the essentials that you need to be able to continue on with your modeling, get you either a refresher or the first introduction to it. Keep in mind that we've got this website set up right now for this concept and for all the others that are coming up. surfacewater.biz/Froude is this one, but we'll do it for each of the others as well. If you have resources you'd like to contribute, let me know and I'll put it on there. And then anybody watching this recording, we get thousands of people watching these recordings on YouTube, can be referred to that, and we can highlight your research or any cool ways you have, any analogies that really help get the point across. That's what we want to do. We want to make this fun for everybody, but informational, and also be able to have you grasp these concepts so that it's not just a bunch of equations coming out there. You actually understand what that means. And sometimes it takes analogies to do that. It takes a mix of the academic world and the practical side of things. And this is a preview of what you'll get in these courses. We're going to try and hit both and get you the best exposure you can to these concepts so that you're comfortable doing that. The courses will include exercises as well. And hands-on interaction with the instructors, where you don't just watch somebody do it, we'll actually have you do it yourself. You're going to compute this and you're going to predict, is this supercritical, subcritical? Where does the hydraulic jump occur? So with that little plug for that course coming up, have a look at all the other things coming up. This recording will be emailed out to you as a link, and you'll get a certificate of attendance. So this does count toward your professional development. And again, to those doing it tough in the world right now with some of the current events, the flooding, some of the instability out there, our thoughts are with you. Fill out our survey. Let us know what you want to hear from next month. Rather than continuing on this series, we're going to actually have a break and talk about how you can help. Humanitarian aid. There's a lot of that needed in the water sector. How can water professionals help? And then we'll get back into this in May and talk about waves, Navier-Stokes equation, and those sorts of things. So with that, thanks all for your participation, to the presenters and panelists. Thanks to the attendees for your questions and this interactive time. It's great to be with you on these seminars. I always look forward to these each month as we do these, and do tune into the TwoFlow webinars coming up in a couple weeks' time as well. So with that, we'll sign off. Thanks so much. See you next time.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative, and critical advances in water science, technology, and management, subscribe now. To build your skills, enhance your technical knowledge, and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.